Hello, welcome to Module 11 of the course on application of spectroscopic methods in molecular structure determination. We will continue with the NMR spectroscopy and look at the use of NMR spectroscopy in stereochemistry determination in organic compounds. Stereochemistry is a very important topic in organic chemistry, and determining the relative stereochemistry or absolute stereochemistry of organic molecules is a very important task in day-to-day research. Now, in this particular module, we will see how stereochemistry of certain molecules can be determined using the delta values and J values, which can be derived from the NMR spectrum. The parameters that are commonly derived from the NMR spectrum are the chemical shift value, the delta value, and the coupling constant value, which is the J value. Both of these parameters can be extremely useful in deciding the stereochemistry of an organic compound. Of course, the third parameter which is derived from an NMR spectrum is the integration, in other words, the area under each of the peak. This is essentially used for quantification purposes. In pure compounds, of course, it tells you the relative intensity, tells you the number of protons under each of the chemically different hydrogens. Of course, in a mixture of compounds, it tells you the mole ratios of the compound present in the mixture. Now, let us look at a very simple example of ketene dimerization. This essentially illustrates how complex an NMR spectrum becomes when the molecule becomes unsymmetrical, or when the molecule is highly symmetrical, how fewer number of lines are seen in the NMR spectrum. Ketene can undergo dimerization. One can conceptually think of the dimerization in two different ways. In one case, two molecules undergo dimerization essentially at the carbon-carbon double bond in a head-to-tail fashion to give this diketone as the product. The other way, one molecule C double bond O and another molecule C double bond C can undergo the 2+2 cycloaddition reaction to give a beta-lactone structure like this one. Of course, if we look at the two structures, this is clearly a more unsymmetrical structure compared to this particular structure. The actual experimental spectrum of ketene dimer is shown on the right hand side here, and you can see here it is a fairly complex spectrum consisting of chemical shift value 1, chemical shift value 2, and chemical shift value 3. Now, if you look at these two structures, this structure should have one chemical shift value corresponding to this hydrogen, which is cis to the oxygen, another chemical shift value corresponding to this hydrogen, which is trans to the oxygen, and finally one chemical shift value for both the methylene hydrogens in this particular molecule. So, three chemical shift value would be anticipated for this structure, and indeed this spectrum gives you the three different chemical shift value roughly in the integration ratio of 1:1:2 ratio is the integration ratio. Therefore, one can confirm that the ketene dimer actually has this kind of a structure. If you look at the other structure, which is a highly symmetrical structure, there is a plane of symmetry passing through this molecule, and there is another plane of symmetry passing through the molecule. There is also C2 axis of symmetry that makes all the four hydrogens chemically equivalent, so it is expected to give only a singlet. Indeed, it does show only a singlet around 3.6 ppm or so in the NMR spectrum. Let us see another example. This is a diethyl diether is what is shown here. The ethyl groups are essentially appearing as a simple quartet and a triplet in the NMR spectrum, and this methylene groups appears as a singlet around 4.5 ppm in the NMR spectrum. Let us see what happens to the spectrum when you introduce a methyl group at this position, how complex the NMR spectrum becomes. This is the NMR spectrum of the diethyl acetal of acetaldehyde. This molecule is nothing but the diethyl acetal of acetaldehyde, and just by introduction of this methyl group here, this methylene groups become diastereotopic. As a result of that, they split each other into a AB quartet, which is further split by the methyl group into a quartet. So, what one sees is a quartet of an AB quartet is what is seen here, and this is a signal that is corresponding to the methylene region, methylene hydrogens of this particular molecule around 3.6 ppm or so, and this region is expanded to show the complexity of the spectrum that is arising out of the introduction of the methyl group at this position. Now, this quartet, which is a simple first order quartet, is essentially for this hydrogen, the methane hydrogen, which is flanked by the two oxygens, and that is further split by the methyl group into a quartet. So, this is an illustration of an unsymmetrical molecule giving a fairly complex NMR spectrum, which is enriched with a lot of information about the structure of the molecule. Now we will take a look at the use of chemical shift value in the determination of stereochemistry with a few examples. Now, due to anisotropic effect of the sigma bond, the axial hydrogen and the equatorial hydrogens appear in different chemical shift value. This is something we have already seen, and we have also explained the phenomena of the anisotropic effect of this particular hydrogen, this particular carbon-carbon bond on the equatorial hydrogen and the axial hydrogen. The equatorial hydrogen is always at a higher delta value compared to the axial hydrogen because of the anisotropy of this particular carbon-carbon bond. This is easily reflected in the spectrum of tertiary butyl cyclohexane, for example. Tertiary butyl cyclohexane does not undergo the chair-to-chair interconversion. Therefore, the hydrogen which is axial and the hydrogen which is equatorial are fixed in their position, and NMR can very clearly tell the difference between these two hydrogen. Now, the equatorial hydrogen appears at 1.62 ppm, whereas the axial hydrogen appears as 1.12 ppm. Of course, there is no stereochemistry associated with the tertiary butyl cyclohexane. On the other hand, if you look at 4-tertiary butyl cyclohexanol or the nitro substituted 4-tertiary butyl cyclohexane, these are the two types of molecules one can consider. The OH group or the nitro group can be either in the axial position. This would be the cis isomer of the 4-tertiary butyl cyclohexanol. The X group, namely the hydroxy functional group or the NO2 group, can be equatorial in position, and this would be corresponding to the trans isomer of the 4-tertiary butyl cyclohexanol or the nitro cyclohexane derivative, 4-tertiary butyl nitro cyclohexane derivative. Now, this would mean that this equatorial group, which is equatorial hydrogen, which is attached to a carbon directly bearing the electronegative center, namely the oxygen or the nitro group in this molecule, this should experience a higher delta value compared to all the other hydrogens in the molecule. So, it should be easy to pick out this particular hydrogen in the spectrum compared to all the other spectrum of the same molecule, for example. When we do so, we identify this hydrogen to be an equatorial hydrogen having a chemical shift value of 3.93, whereas in the axial isomer, namely the axial hydrogen isomer, corresponds to a chemical shift value of 3.37. So, if whenever one encounters this kind of molecules, the one that is showing a higher delta value for this particular hydrogen would correspond to the axial X or the equatorial hydrogen isomer. The other isomer, namely the one with the lower delta value, will have the hydrogen in the axial position or the substituent in the equatorial position. This is illustrated by these two examples very clearly, showing that the cis configuration, namely the tertiary butyl and X being cis, has a higher delta value, whereas the tertiary butyl and X being trans with respect to each other has a lower delta value in the NMR spectrum, which is very useful for the identification of the cis-trans isomer. These are essentially diastereoisomers, cis isomer and the trans isomer. They can be easily distinguished purely based on the chemical shift value of the hydrogens, which are distinguished as equatorial or axial in nature. Now, sugar chemistry is rich in stereochemistry, and it is important to determine the stereochemistry, absolute stereochemistry as well as the relative stereochemistry of sugar molecules. Let us take the methyl glycoside of glucose, for example. This is not glucose, I am sorry. This is galactose. This is a methyl glycoside of galactose is what is shown here in this particular spectrum. And if you look at this particular hydrogen, this is the anomeric hydrogen. When the methoxy is in the axial position, the anomeric hydrogen is in the equatorial position. Similarly, when the methoxy is in the equatorial position, the anomeric hydrogen will be in the axial position in the chair form of the 6-membered ring, which is the sugar ring that is shown here. As a pyranose ring is what is shown here. Now, we can very clearly see that the hydrogen, when it is in the equatorial position, it is coming at a higher delta value of 5.18 compared to hydrogen which is in the axial position, which is coming around 4.69. If you look at the molecule, the blue hydrogen is the one that is going to come at the highest chemical shift value, and hence we are able to distinguish between the equatorial isomer and the axial isomer very clearly from the chemical shift value of the hydrogen. Not only from the chemical shift value of the hydrogen, the methoxy group also plays a role in determining the stereochemistry. The axial methoxy group, for example, comes at a lower delta value compared to a equatorial methoxy group around 3.97, once again due to the anisotropic effect of this carbon-oxygen bond, which is beta gamma from the position from where the measurements are being made. This is another example again showing that in the carbon spectrum, the axial CH2 and the equatorial CH2 can be distinguished. The axial CH2 carbon comes at a lower delta value compared to the equatorial CH2 carbon, which comes as a higher delta value, for example, in the carbon 13 spectrum of the compound, which is this dicarboxylic acid, cyclohexane dicarboxylic acid. Now, anisotropic effect of carbonyl groups can play a very important role in determining the stereochemistry of this kind of exocyclic double bonded compound. This is nothing but an enol ether of the alpha formyl tetralone, which is the molecule here. This hydrogen actually feels the anisotropic effect of this particular carbon oxygen double bond and comes in the de-shielding zone of the anisotropic effect of the carbon oxygen double bond. So when it is cis with respect to the oxygen of this particular carbonyl functional group, it comes at a higher delta value of 7.85 ppm, whereas when it is trans to the carbonyl functional group, it comes around 6.35 ppm. In other words, this does not have the same facility of feeling the anisotropic effect of the carbonyl functional group when it is trans compared to when it is cis compound. The same effect is seen instead of hydrogen if you have a methyl substituted derivative. This is a 2-acetyl tetralone enol ether is what is shown in this particular spectrum. The particular structure corresponds to the enol ether of the 2-acetyl tetralone as a molecule. In this particular case also, this methyl which is cis to the carbonyl functional group comes at a higher delta value compared to the methyl which is trans to the carbonyl functional group, which comes at a lower delta value. Now, when the hydrogen is placed exactly on top of a carbon-carbon double bond or an aromatic ring, it gets highly shielded because of the anisotropic effect of the double bond, which is a shielding zone above and below the double bond and a de-shielding zone on the periphery of the double bond. So, if you look at this bicyclic alcohol 2 isomers that are shown here, this would be an exoisomer with respect to the double bond, and this would be an endoisomer with respect to the double bond. The exoisomer has the hydrogen lying above the carbon-carbon double bond. Therefore, this must be shielded in nature. So, that comes at a lower delta value of 3.53 ppm, whereas the one which is an exo compound, which is the exohydrogen with respect to the double bond, that does not have the facility to feel the anisotropic effect of the carbon-carbon double bond, which is further away from the hydrogen. So, this comes at a higher delta value in relation to this one. In all of these cases, it would be nice if both the isomers are available and the stereochemistry can be determined by measuring the spectrum of the two compounds and looking at the chemical shift value of both the isomers. It may not be easy to, if you have only one isomer, to decide on the stereochemistry of that particular isomer purely based on the chemical shift value that we are discussing here. Now, let us move on to using J value for the determination of stereochemistry. It is very clear that stereochemical aspects arise because of the orientation of the molecule in certain ways, and this orientation is essentially decided by the dihedral angle when you have vicinal hydrogens of this kind. So, one can use the vicinal coupling constants as a tool for determining stereochemistry of certain molecules, and let us see some examples of this. This curve you are already familiar with. This is called the Karplus-Conroy curve for the dihedral angle dependence of the vicinal coupling constant, which is a 3-bond coupling, and the vicinal coupling 3-bond coupling is what is pictorially shown here, and this corresponds to the dihedral angle that we are referring to in the figure where dihedral angle is plotted against the J value. Now, if you take a highly symmetrical molecule like this dichloroethylene cis and trans isomer, the dichloroethylene cis and trans isomer, or the cis-stilbene trans-stilbene kind of molecule, these two hydrogens do not couple with each other. As a result of that, we are not able to use the J value to determine the stereochemistry of this class of molecules. Let us have a look at the NMR spectrum of the cis-stilbene. Cis-stilbene, the olefinic hydrogen comes as a sharp singlet and does not have any kind of a signature of coupling with other hydrogen. Similarly, in the trans isomer also, the trans-stilbene the olefinic hydrogen come as a singlet in the trans-stilbene also. Nevertheless, the cis-stilbene and trans-stilbene can be distinguished based on the chemical shift value. The cis-stilbene has a lower chemical shift value around 6.6 ppm, whereas the trans-stilbene has a higher chemical shift value for the olefinic hydrogen, which comes around 7.1 ppm or so. It may not be easy to do this with the derivative which is dichloroethylene, for example, because dichloroethylene does not have this kind of an anisotropic effect to distinguish the two hydrogens from the cis and trans isomer. Now, if you look at the cis stilbene oxide as well as the trans stilbene oxide, again essentially one cannot determine based on the J value because there is no coupling between these two hydrogen because of the symmetrical nature of this molecule. In the cis trans isomer, the two hydrogens come at 3.9 ppm or so, whereas in the cis isomer here it comes around 4.2 ppm or so in the NMR spectrum for the two hydrogens, which are the epoxide ring hydrogen in this molecule. That is why we use the carbon-13 satellite spectrum. This is something we have already discussed earlier, but let me refresh your memory that the carbon-13 satellite spectrum is nothing but a proton spectrum of the compound where the carbon-13 is in its natural abundance. So, since the natural abundance of carbon-13 is 1%, if you take a molecule like dichloroethane, this would be 99% of the molecule that we take, whereas 1% of the molecule will be naturally labeled by a carbon-13 labeling in this position. The carbon-13 label makes this molecule unsymmetrical in terms of the magnetic equivalence as well as chemical equivalence of these two hydrogens, for example. These two hydrogens are chemically equivalent still, but magnetically non-equivalent because we have introduced another magnetic nuclei, which is a carbon-13 nucleus in this particular case. So, what happens to this molecule? The NMR spectrum of this molecule will, this hydrogen, if you take, it will be split by the carbon-13 by a large coupling constant of nearly 100 Hertz or more. That will be a large coupling, and this coupling, this hydrogen will be further split by the trans hydrogen because these two hydrogens are now magnetically non-equivalent. What was originally magnetically equivalent becomes magnetically non-equivalent. This should be a prime system rather than a AM kind of a system. There is a mistake here, please correct it. And essentially a doublet that is split by the carbon-13 splitting of this HA hydrogen into a doublet will be further split by HM into a doublet. So, this will be a doublet of a doublet is what one sees. This is the centers where this compound spectrum essentially comes as a singlet at the center of the spectrum here, which is shown here, for example, whereas this molecule spectrum essentially will be split into a doublet by carbon-13 coupling and further doublet into this H coupling, which is this particular coupling. Similarly, if you take this hydrogen, this will be split by the carbon-13 into a smaller coupling constant because it's a 2-bond coupling now, and it will be further split by the HA into a doublet. So, doublet of a doublet is what is seen for HM, which is this spectrum here, and HA, which is this part and this part of the spectrum corresponding to HA. So, if you measure the coupling constant between these two lines here, that would be essentially JAM. Similarly, if you measure the coupling constant between these two lines here, that will also be JAM. The experimental spectrum is shown here nicely. Here, the carbon-13 lines are very weak because it is only 1% of the sample that contains the carbon-13 labeling. So, one need to do large number of scans to minimize the signal to noise ratio and look at very carefully on either end of the main spectrum. This is the main spectrum corresponding to this compound, which does not have any carbon-13, and the satellite peaks are shown, and it is zoomed into a larger peak in terms of the visibility of this doublet of a doublet that we see here. So, the carbon-13 J value is this gap, and the hydrogen J value is this gap. Once you have the hydrogen J value, one can easily tell whether it is a cis isomer or a trans isomer, because trans isomer should have typically between 15 to 18 Hertz as a J value, whereas the cis isomer will have a J value of roughly around 10 to 12 Hertz or so. So, here is another example indirectly deriving the J value from the carbon-13 satellite spectrum to decide on the stereochemistry of compounds, which cannot be determined purely based on the delta value alone. As long as we are speaking about carbon-13 spectrum, one can also label the compound with carbon-13. This is an example which appeared recently in the Journal of Organic Chemistry, for example. We are looking at only the benzylic hydrogen of styrene. This is not ordinary styrene. This is a styrene which is labeled 50% by carbon-13 labeling at this position here. That means you have a 1:1 mixture of carbon-12 and carbon-13 styrene, where the labeling is very specific to this particular carbon, which is the alpha carbon in this molecule. Now, what happens to the hydrogen A is what is shown here. The benzylic hydrogen, which is hydrogen A, that is a spectrum. This is the spectrum corresponding to the carbon 12 molecule, because the HA should be split into a doublet by the trans hydrogen and further into a doublet by a cis hydrogen. So what you see for HA is the doublet of a doublet, which is the main spectrum as far as this molecule is concerned. The satellite spectrum, which is specifically labeled to an extent of 50%, that is the reason you have very high intensity of the satellite peaks here, because this is a labeled compound. So 50% of the molecule has this carbon, which is carbon 13, that should couple with HA into a doublet. So you see this large coupling which corresponds to the carbon 13 HA. Further down, the HA should be split by this hydrogen, which is a cis hydrogen, and this hydrogen, which is a trans hydrogen. So because of carbon 13, it will be a doublet. Because of the trans coupling, it will be a doublet of a doublet. Because of the cis coupling, it will be a doublet of a doublet of a doublet. So essentially what you see is a 8-line pattern, which is a doublet of a doublet of a doublet for this particular hydrogen in this molecule. This is essentially illustrate the point that one can synthetically make samples with carbon 13 labeling and look at the satellite spectrum in a much more prominent way compared to the natural abundance carbon 13 spectrum. The bromostyrene can exist in 3 different forms. This is the trans isomer, this is the cis isomer, and this corresponds to the alpha isomer. These two are beta isomer, whereas this is alpha isomer. This is a spectrum of the alpha isomer that is shown here. The olefinic hydrogens, which are HA and HB, comes very nicely as a AB quartet in this molecule. And if you look at the coupling between these two lines here or these two lines, it should be identical. There is a very small coupling. This small coupling is essentially indicating that this is the particular isomer spectrum that is shown in the picture here. The spectrum, the J value essentially corresponds to 2 Hz, and the 2 Hz essentially corresponds to an sp2 substituted with a geminal dihydrogen, this kind of a dihydrogen derivative which is geminal, and it is also sp2 in nature, essentially gives a coupling constant value of 2. If it is a cis isomer, coupling should be around 10, whereas the trans isomer typically coupling should be around 15. You can see the trans isomer in this particular case with the larger coupling. You can see compare the spectrum, this spectrum with the smaller coupling and this spectrum with the larger coupling. This corresponds to the trans isomer of the beta bromostyrene in this particular case. Another example to illustrate the use of the coupling information, namely the trans coupling, is what is seen here. This hydrogen should be a doublet, this hydrogen also should be a doublet, and this hydrogen essentially, which is right next to the carbonyl functional group, this is actually a push-pull kind of a system. The sulfur lone pair can be delocalized onto the COOH group. So this hydrogen, which is in the beta position and also close to the sulfur, comes at the higher delta value around 7.9 ppm or so, whereas this hydrogen comes, which is alpha hydrogen, comes around 5.6 ppm or so. And this trans coupling is measured by measuring the gap here or measuring the gap here, which corresponds to 14 Hz. And 14 Hz is typically 14 to 18 Hz is typically the trans isomer. Anything less than 12 Hz is taken as the cis isomer. Now earlier we saw the glucose derivative, which is identified on the basis of the chemical shift value of the anomeric hydrogen. One can also use the coupling constant of the anomeric hydrogen to determine the stereochemistry of this molecule. Let us take glucose pentaacetate, both the alpha anomer as well as the beta anomer. This is the beta anomer of the pyranose ring that is shown here, and this is the anomeric position carbon. So if you look at this particular hydrogen, this has a coupling partner which is in the adjacent carbon, so it is a vicinal coupling between these two. The dihedral angle between these two hydrogens are about 60 degree. So one would expect around 2 to 6 Hz is the coupling constant value between axial and equatorial hydrogen in the terms of the vicinal coupling that one can see. The spectrum is shown here. The spectrum is fairly complex because these hydrogens are second order pattern hydrogen. But what is easy to identify is the anomeric hydrogen, which comes as the higher delta value, which is around 6.2 or 6.3 in this particular case. And this is appearing as a doublet because of the vicinal coupling, and the coupling constant that is measured is the gap between these two lines that is shown as a doublet here in this region of 6.3, and that corresponds to 3.9 Hz. So as a result, we conclude that this would be the this is actually the alpha isomer of the pentaacetate of glucose. If you look at the beta isomer, which is this particular isomer, the dihedral angle between these two hydrogens should be 180 because they are trans and they are diaxial in nature. The dihedral angle is 180, which will have the maximum coupling constant in the range of 10 to 14 Hertz or so. This is the anomeric hydrogen in this molecule, which is coming at a lower delta value, because remember the axial hydrogen will come at a lower delta value compared to the equatorial hydrogen, which comes at a higher delta value. So in addition to using the delta value, which is high for the equatorial hydrogen and low for the axial hydrogen, one can also use the vicinal coupling between the anomeric hydrogen and the adjacent hydrogen if the adjacent hydrogen is present in the molecule. Then also one can derive at the stereochemistry. In this particular case, the gap between these two lines, which corresponds to the diaxial coupling, it corresponds to about 9.2, which is expected in the range of about 10 to 14. 9.2 is close enough. So this is a larger coupling compared to the earlier example of the alpha isomer. So the alpha beta anomers can be easily distinguished based not only on the chemical shift value but on the coupling constant values as well. Some more examples of the cyclohexyl derivative, the corresponding, earlier we saw the alcohol, here we are seeing the acetate, but we are looking at the coupling constants here rather than the chemical shift values of these hydrogens. Now we are looking at the coupling between this hydrogen and this hydrogen, or this hydrogen and this hydrogen. The axial coupling is about 11.4. The axial equatorial coupling is 4.2. Whereas in this case, for example, there is no axial coupling. There is only a equatorial and equatorial axial coupling, which are much less than 10 or so. So one can easily distinguish between these two molecules based on the coupling that one sees for this particular hydrogen, which will be a doublet of a doublet in this particular case, because of these two hydrogens splitting it into a doublet of a doublet. That spectrum is not available, so I am just putting the values that are given in the literature as far as the coupling constants are concerned. So this is another example, a molecule where the stereoisomers, namely the trans isomer and the cis isomer of the 4-tertiary butyl cyclohexanol acetate, is distinguished based on the purely on the coupling constant values rather than the chemical shift values. Let us look at an interesting example of cyclization by means of a nucleophilic substitution reaction. This amino alcohol is treated with methyl iodide. Upon treating with methyl iodide reacts with this tertiary amine and forms a quaternary ammonium salt. So you will have NCH3 three times the iodide. The iodide will be the counter ion. When the molecule is heated, the oxygen lone pair essentially attacks this benzylic position and trimethylamine is eliminated in the process. So essentially nucleophilic substitution followed by the trimethylamine as a leaving group is the reaction that you are looking at. But in order for the oxygen to substitute at this position, this carbon-carbon bond should undergo a rotation, and that is why you see the stereochemistry of these two, in this particular case the stereoisomer, for example. The product, you see the two phenyl cis to each other, whereas if you take the opposite diastereoisomer, namely the erythroisomer of the molecule, the oxygen, when the carbon-carbon bond rotates, these two phenyl group becomes trans with respect to each other in the product. So if you observe the stereochemistry of the starting point and the end point, essentially there is a carbon-carbon bond rotation that is taking place. This is a freely rotating bond, so the oxygen, in order to attack this particular carbon, should undergo a carbon-carbon bond rotation, and the oxygen should come here in order to attack this particular carbon. So what happens in the stereochemistry of the product that is formed? How do we find out which isomer is formed? This is the cis isomer, where the two hydrogens are cis with respect to each other. This is the trans isomer, the two hydrogens are trans with respect to each other. The dihedral angles are clearly very different in these two cases. This will have a larger dihedral angle. As a result of that, it has a larger coupling constant. So one can look at, this would be a doublet and this also would be a doublet. This would be a AB system in both cases, and the AB system, the coupling constant is based on the coupling between these two hydrogen. One can easily identify the trans isomer to have the larger coupling constant compared to the cis isomer, which has a lower coupling constant. So in the case of aliphatic system, where there is a free carbon-carbon bond rotation, this is the example of the erythro and stereoisomer of the amino alcohol that is shown here. This particular isomer is the stereoisomer and this particular isomer is the erythroisomer of the molecule. In the stereoisomer, if you look at, there are three conformations that I have written here. These three conformations, two of the conformations have intramolecular hydrogen bonding facility between the nitrogen and the OH, and that will give added stability to that particular conformation. Finally, this is a conformation where the amino group and the OH are anti with respect to each other, so there is no possibility of formation of an intramolecular hydrogen bonding facility in this particular case. If you look at this particular conformation, here the bulky groups are farther away from each other. This is the best possible configuration that one can have, including the stabilization because of the hydrogen intramolecular hydrogen bonding. And if you look at the dihedral angle between these two hydrogens, this is anti, is 180 with respect to the two hydrogens being anti to each other. So as a result, one would expect a large coupling constant if this were to be the most populated state among the three conformers that you have shown here. Clearly, this particular conformer will be the least stable conformer because all the bulky groups are right next to each other. Gaussian interactions are very severe in here. And this is relatively also speaking a easy unstable isomer. Nevertheless, it has a contribution from the intramolecular hydrogen bonding. So among the three, this is expected to be the most stable. Indeed, if this were to be the most stable, this vicinal coupling should be a large coupling. The experimentally observed coupling is about 10.5 Hertz, and this is anti-coupling, expected coupling theoretically based on the Karplus-Conroy equation. It is about 11 Hertz or so, and this is being close to the experimentally observed 10.5. One concludes that this conformer is a major conformer in the mixture of conformers that you can have in the solution phase. It is estimated to be about 90% populated compared to the other two isomers, which are about less than 10% populated. But when you come to the erythroisomer of the molecule, the possibility of having all the three equally populated exists in this particular case because of the intramolecular hydrogen bonding in these two systems. And if you look at this one, this is the anti-conformer. The anti-conformer essentially derives no stabilization whatsoever from the intramolecular hydrogen bonding, just as in the case of this. So one can expect these three, which are relatively speaking less stable compared to these three, to be equally populated in this particular case of erythroisomer. The experimentally observed J value between these two vicinal hydrogen is about 4.4. So this is estimated to be about contributing to about 75% of the mixture of these two with internal hydrogen bonding interaction, and to an extent of about 25% of the non-hydrogen bonded Gaussian isomer in this particular case. So essentially this tells us that the thermodynamically more stable isomer is the stereoisomer with the anti-conformation of these two hydrogen, resulting in a large J value compared to the erythroisomer, which has a smaller J value. So you are using the J value not only to determine the stereochemistry, but also to predict the relative concentrations of the various conformers in solution. In fact, NMR spectroscopy is one of the most widely used spectroscopic technique to not only identify the conformers, but look at the relative populations of conformers in equilibrium in solution. Another example, this is a dibromocinamic acid derivative, dihydrocinamic acid derivative. This molecule, again, the most stable conformation where the two bromines are anti with respect to each other. Hence, the two hydrogens are also anti with respect to each other in the stereoisomer. And the experimentally observed chemical shift, the coupling constant value between the vicinal hydrogen is about 12 Hertz. This is an NMR spectrum of this compound. This hydrogen and this hydrogen forms an AB quartet, which is shown here. And the CH2 of the ethyl ester group is a simple quartet, which is this particular signal here. So essentially, from the coupling information, you come to the conclusion that this is the most predominant isomer in the solution of the three conformers that are written in this particular molecule. So what we have seen here is a few examples of identifying stereochemistry, particularly cis-trans isomer stereochemistry, or diastereomeric isomers stereochemistry, or conformational isomers using NMR spectroscopic technique. And we have used in some cases the delta value or the chemical shift value to distinguish the stereoisomers. Some other cases, few examples are also shown where J values, namely the vicinal coupling information, is used as the tool for identifying the relative stereochemistry of organic molecules. These are some reference textbooks that I have used to collect information for this particular lecture. If you want to refresh your memory on the stereochemistry of organic compounds, I recommend that you read the book by Nasipuri. That is an excellent source of information as far as organic stereochemistry is concerned. Finally, these are again two more books that are available readily for reference in terms of looking at some NMR spectra and looking at stereochemical aspects of NMR spectra. Finally, I would conclude the lecture by thanking all of you for your kind attention. Thank you very much.